Okay, this is a unique problem I made up. Here I have 100 newtons, but it's being applied at a point. Now the point here is going to be not on any of these axes that run through the centroid. So now what you're going to have to do with a situation like this is you have two moments. You have a moment that's going this way, and you have a moment that's going back this way. So we have, we'll call this M1, and we have M2. So as a result of that, what you would have in this situation, you'd have your major compression right here. Because you have this moment creating it, it's trying to compress here, you have this moment trying to compress here, and you have this force here. So now to find, if you're given a problem like this, first thing to do, let's talk about this. First thing I would do, I would find out what the area is. Now, you don't have to do the centroid because we know the centroid is located right here. This part is just a rectangle. So we'll find the area, and the area here is going to be 0.100 times 0.075. We'll calculate that very quickly. And we do that, that'll give us the area 0.0. Oops, hang on a second. 0.75. Got a little delay with this system, so bear with me there. And that should be millimeters, sorry. And that would give me the meters square. Alright, now on this one you're going to have to find two moments of inertia. If you're going to do this one here, you're going to let this be the base and you're going to let this be the height. So we'll call, let's call this, we'll define these axes. I'll call this my x-axis. We'll call this the z-axis. So we'll call this ZZ and we'll call this XX. So I would do the moment of inertia about ZZ. To do that, I'm going to do 1/12 times my base times my height, which is going to be 0.1. Again, sorry about this delay, 1 cubed. And that was what that value would be. And I run that, 1 divided by 12. Times 0.075 times 0.10 to the third power. That's going to give me a value of 6.25 times 10 to the minus 6. And again, that's going to be meters to the fourth. Man, this thing is really bad tonight. Okay. Now I will find the moment of inertia about the XX. (1/12). Now I want to find about the XX. My base is going to be 0.1. My height's going to be 0.075 cubed. So 1 divided by 12 times 0.1 times 0.075 to the third power gives me a value of 3.51. Five, 6, 3, 1, 5, 6 times 10 to the minus 6. Well, here we go. Alright, so if I'm going to find out the area of this, let's call this area. If I'm going to find the stress at A, then what I would say here would be the stress at A would equal to the load that's been applied divided by the entire cross-sectional area, which is 0.075, plus my moment. And my moment in this case, let's do we'll do M1 here, a moment around the z-axis. So I'll label it here MZ. Moment Z is going to equal to 100 times 0.020. So 100 times 0.02. That gives me 2 Newton meters. My moment about around the x-axis is going to be 100 times my moment arm, which is 0.001, and that equals to 1 Newton per meter. So if I'm going to do, we'll do this one first. We go to moment around z, we get 2. So now I'm doing this moment, and this distance from here to here is going to be your c value. That'd be 0.02. I divide it by the moment inertia, and it's going to be the moment inertia around the z. So that would be 6.25 times 10 to the minus 6. Now you do plus, and the moment's going to be 1. And you got the 1 coming here. The c value here would be 0.01. Oops. Again, really, I have to shut this system down so I don't keep having these kind of issues. I'll scroll up a little bit, and then we'll divide by 3. 3.516 times 10 to the minus 6. If I ran that number, that's going to give me the maximum stress, and that's going to be at A. Now let's just talk about this. If I was going to find out what the stress would be at B, I would, again, what I would do, I'm going to talk through this. I'm going to take this force, I'm going to divide it by this entire cross-sectional area here. Now this one is going to cause more compression, so I would take 100 divided by this area times this m value times the distance from here to here divided by the moment inertia around x. That would be added together because they're both causing compression, and then I would subtract this moment times the distance from here to here divided by the moment inertia around z. That would give me the value at B. Now let's just say I want to find out what the stress would be at C. Be 100 divided by the entire cross-sectional area. Both of these moments are creating tension. So again, I'll repeat, 100 divided by the cross-sectional area. I would make that, we could make that positive, whatever, and I would subtract this moment times this distance divided by the moment inertia around the x-axis minus this moment times this distance here divided by the moment inertia around the z-axis, and that would give me the value here. And I would just note that even though I'm making them negative, I would say, well, that's going to be tension, because both of these moments are creating tension. This is causing compression. I don't get too tied up around about the signs. I just I look, because if I'm going to make 100 divided by the area as being positive, then that means that's compression, and then anything that comes up negative would be tension. So if my answer comes up negative, then I know it's in tension. My answer comes up positive, then I know it's compression. Same way, if I want to find out what the stress would be here, we'll call this at D. It'd be 100 divided by the entire cross-sectional area here. This is causing compression plus M1 times the distance from here to here divided by the moment inertia around the z-axis. And then I would subtract, because this one's pulling away, the moment here times the distance from here to here, which is my c value, divided by the moment inertia around the x-axis, and that would give me the value of D. So anyway, I hope that helped. Again, this is a little unusual, but this is a possibility for a test question where the load is being applied, but it's not going to be on one of the axes. In this case, you've got to consider both moments of inertia, and you have two different c values.